Hi guys, in today's video we will be discussing quantitative aspects of chemical change, grade 11 chemistry. Let's get to it. We have three subsections in this chapter, that is gases and solutions, stoichiometric calculations, and volume relationships in gaseous reaction. First, let's discuss gases and solutions. Let's analyze gases and solutions and how to solve problems around or related to them. First, we have molar mass of gases. With our knowledge of gases, we can calculate the volume of 1 mole of gas at standard temperature and pressure, otherwise known as STP. First, we have pressure, symbolized by small letter p, which is equal to 101.3 kilopascal or 101,300 pascals. Next, we have number of moles, which is represented by a small letter n, which is equals to 1 mole. Next, we have universal gas constant, which is equals to R, which is equals to 8.31. And lastly, we have temperature, which is equals to 273 Kelvin. And we're going to substitute that into our ideal gas equation, which states that PV is equals to nRT. And hence, substituting in my values, I will have 101,300 V is equals to 1 times 8.31 times 273. And hence, making volume subject of the formula, I will have V is equals to 1 times 8.31 times 273, all divided by 101,300, which will give me a volume value of 0.0224 centimeters cube. And I'm going to convert that into SI unit, which is decimeters cube, which is equals to 22.4 dm cube. You just multiply by 1000 and you will get 22.4 decimeter cube. And hence, this is for 1 mole. And for multiple moles, we're gonna substitute in the n to give us volume of gas is equal to 22.4 multiplied by number of moles of that gas. This is at standard temperature and pressure, otherwise known as STP, for gases. Let's move on. Now we're gonna analyze reactions and gases. For a reaction between gases, we can calculate the volume of the gases because the volume is proportional to number of moles. And hence, volume of A is equal to A over B multiplied by VB, where VA is equal to volume of gas A, VB is equal to volume of gas B, and A is the stoichiometric coefficient of gas A, and lastly, B is the stoichiometric coefficient of gas B. Moving on, let's take a look at an example. Hydrogen and oxygen react to form water according to the following balanced equation. If 5 dm cube of oxygen is used, what volume of water is produced? Let's take a look at how we solve this one. First, I went on and calculated or determined my stoichiometric ratio of between oxygen and water. Oxygen is my reactant and water is my product. And if I look at my balanced equation, before the oxygen, there is no value and hence it's 1. And before the oxygen on my product rather, there is a 2, which means it's 2. And hence the volume of oxygen to water is 1:2, according to my balanced chemical reaction. And now I'm going to go on and say VA is equal to A over B, VB. For VA and VB and A and B, you can choose either the reactant or the product to be either. But if you choose VA as the reactant, the A will need to be of that of the reactant as well, and vice versa. In this example, I chose my VA as what? As 5, and hence as that of the reactant because that is what I am given. And hence I went on to say 5 is equals to, and because the ratio of oxygen is 1, I started with 1 on A and divided by ratio of water, which is 2, divided by 2 is equals to multiplied by VH2O, which is the volume of water. And making the volume of water subject of the formula, I multiply both sides of the equation by 2, and I will get the volume of water, which is equals to 10 dm cube. And that is how you solve that particular problem. Now let's move on to solutions. Under solutions, we have concentration, which is the amount of solute per liter of a solution. And to calculate concentration, we go on and say C is equals to N over V, where C is obviously our concentration, N is the number of moles, and V is our volume. And now let's define titration. Titration is the process of calculating the concentration of an unknown solution. And the following formula can be used to reduce the number of titration calculations that we need to do in order to calculate that number of moles, or that concentration rather. We go on and say CAVA all divided by A is equals to CBVB all divided by B, where A and B are our stoichiometric coefficients of compounds A and B respectively. Now let's take a look at the following example. From the equation that you can see on my screen, we have 20 centimeter cube of a 0.5 moles per dm cube nitric acid solution was pipetted into a conical flask and titrated with potassium hydroxide. It was found that 25 centimeter cube of potassium hydroxide was needed to neutralize the acid. Calculate the concentration of the potassium hydroxide solution. Let's take a look at how we solve this one. First, we went on to say for KOH, we have a volume of 25 centimeter cube, and we went on to convert that to SI units dm cube and divided by 1000 to give us a volume of 0.025 dm cube. And now we're going to go and analyze HNO3. We have a volume of 20 centimeter cube, which we divided by 1000 to get a volume of 0.020 dm cube and a concentration of 0.5 mole per dm cube. Now we're going to introduce our formula that we learned previously, CAVA all divided by A is equals to CBVB all divided by B. And substituting in our values, we'll have the following on my screen there. The ratios are 1:1, and hence A and B are both 1, and hence we will have 0.025 multiplied by the concentration of KOH is equals to 0.01, and hence making concentration the subject of the formula, will have C KOH is equals to 0.01 all divided by 0.025, and that will give us a concentration of 0.4 moles per dm cube, and that is how you solve that particular problem. Let's move on. In grade 10, you learned how to write balanced chemical reactions. If we know the ratios of substances in a balanced reaction, stoichiometry makes it possible to calculate the amount of either reactants or products that are involved in that chemical reaction. First, let's define limiting reagent. That is a reagent or a substance that is completely used up in a chemical reaction. It finishes up first. Next, we have excess reagent, which is a reagent or a substance that is not completely used up in a chemical reaction, and hence it remains after a reaction. So, if so far you are finding this video a little bit tolerable and helpful, please head to our website using the link in the description below, and from there you can select the menu, select your subject, select the paper of the subject that you want to study, and from there you will find the subject materials from videos to presentations. Presentations are notes I use on lessons, including the notes of this lesson. You can find them on our website, which is completely free. Even the notes, you can find them there for free. You don't need to take screenshots. Just head to our website and download the notes for free. And when you're done studying, you can take the quiz. You just select it, and it's time limited, 15 minutes, and you take the quiz. And when you're done taking the quiz, it will show you your score along with the memo. And if you feel like you're confident, you can try the quiz again. If you got total, you can always move on. But if you feel like you want to try again, you can just try again, or go back to the paper, as you can see. So please head in the link in the description to find some cool study materials. Thank you. Let's take a look at the example. Nitrogen gas reacts with hydrogen gas to produce the fertilizer ammonia NH3 according to the following balanced chemical equation. What is the maximum mass of ammonia that can be obtained from 5 kg of nitrogen gas and 2 kg of hydrogen gas? Let's take a look at solutions. First, we calculate the number of moles of nitrogen and hydrogen. And the number of moles of nitrogen is equal to mass over molar mass, which is equal to 5 multiplied by 1000 because we are converting it to grams, and 2 multiplied by 14, which is the molar mass of nitrogen on the periodic table. And that will give us a molar mass value of 5000 divided by 28, which is equal to 178.57 moles. And next we calculate the number of moles of hydrogen, which is equal to mass over molar mass, which is equal to, again, 2 multiplied by 1000 multiplied by 2 multiplied by 1, because that is the molar mass of hydrogen on the periodic table, and that will give us 2000 divided by 2, which is equal to 1000 moles. And now we're going to go on and determine which between nitrogen and hydrogen is our limiting reagent. First, we went on and found the ratio between nitrogen and NH3, as you can see, which is equal to 1:2, because before nitrogen there's nothing and hence it's 1, and before NH3 or ammonia is 2, and hence the ratio is 2, and hence the combined ratio is 1:2. Next, we're going to go on and say the number of moles of ammonia that can be produced from the provided nitrogen is equal to number of moles of provided nitrogen multiplied by ratio or stoichiometric ratio or molar ratio, or however you want to describe it. And substituting in the values, we'll have 178.57 multiplied by 2 divided by 1. And that will give us the number of moles of 357.14 moles. Next, we're going to go on and calculate the number of moles of ammonia that can be obtained from the provided hydrogen. And we're going to go in on and say the number of moles of ammonia is equal to number of moles of hydrogen multiplied by stoichiometric ratio. And substituting in our values, we'll have 1000 multiplied by 2 over 3, because the ratio is 2:3, as you can see, or 3:2. And we start by the ratio of the products on the numerator and the ratio of the reactants on the denominator, and hence it will be 2 divided by 3, and that will give us a value of 666.67 moles. And between the number of moles of ammonia that was provided by our hydrogen and the one that was provided by our nitrogen, the one that was provided by nitrogen is lower than that provided by hydrogen, and hence in this case nitrogen is our limiting reagent, and hence the maximum mass of ammonia that can be produced will be determined by the limiting reagent, which is our nitrogen, which is the number of moles of the value equal to 357.14 moles. Now we're going to go on and calculate the mass of ammonia that can be produced from the number of moles that is produced from the limiting reagent. And we're going to go on and say mass is equal to number of moles multiplied by molar mass. That is the number of moles equation we just made more mass subject of the formula this time around. And substituting in the values, we'll get the mass value of 357.14 multiplied by 14 plus 3, which will give us 357.14 multiplied by 17, and hence that will give us a mass value of 6071.38 grams, and converting it to grams, it will give us a mass of 6.07 kilograms, and we've answered that particular question. Let's now move on to percentage yield. Percentage yield is very important in chemistry because it tells us how efficient the reaction is. A reaction with higher percentage yield uses most of the reactants to produce the desired products, and one with low percentage yield uses less of the reactants to form the desired products and results in higher amounts of waste products. The formula to calculate the percentage yield is Percentage yield is equals to actual yield divided by theoretical yield, all multiplied by 100. Now let's take a look at an example. Nitrogen gas reacts with hydrogen gas to produce ammonia according to the following balanced chemical equation. It's the same equation as the previous one. A chemical engineer carries out a reaction using 5.6 kg of nitrogen gas and 1.5 kg of hydrogen gas and collects 5.1 kg of ammonia. What is the percentage yield of this reaction? Let's take a look at the solution. We first determine the limiting reagent as we've always done, and we know that the maximum number of moles of ammonia that can be produced in this reaction is 357.14 moles, and the maximum mass is 6.07 kilograms as per the last examples, because the values are still the same, and hence we're going to use the same values. But if those values are not provided or you haven't calculated for them before, you need to start from scratch, doing it like we did in the previous example. Now we're going to go straight into calculating our percentage yield and substituting in the values that we now have. The actual yield is 5.1 kilograms. That is the mass that we were given by the problem statement, and 6.07 is the calculated mass from previous example, and we're going to multiply that division by 100 to get a percentage yield of 84%. Fairly efficient reaction, if you ask me. Now let's move on to molecular and empirical formulae. Empirical formula is the simplest whole number ratio of atoms present in the compound, whereas molecular formula tells us the exact number of atoms in the compound. To explain this difference a little bit better, let's use glucose. We know that the molecular formula of glucose is C6H12O6. Now, the empirical formula makes that formula a little bit more simple by dividing everything by the lowest common factor, which is 6, and hence the 1 of carbon divided by 6 will be 1, and hence it will just be C, and 12 divided by 6 will be 2, and hence it will become H2, and O divided by 6, it will be still remain SO, and hence the empirical formula is CH2O. Note that the empirical formula, it doesn't tell us how many carbon atoms, hydrogen atoms, or oxygen atoms are there in that compound. It just gives us a ratio of one into another. But the molecular formula gives us exact number of atoms, not simplified, not deduced into a ratio. Now let's define percentage composition. Percentage composition is the percentage by mass of each element present in a compound. It tells you how much of a compound total weight comes from each individual element. For example, water is 89% oxygen and 11% hydrogen. That is because in the periodic table, oxygen has higher molar mass than hydrogen, which is just 1. Oxygen is 16 if I'm not mistaken. Now let's take a look at an example. A whiteboard cleaner, which is used in classrooms and offices to remove stubborn marker stains and ghosting, is a dilute form of isopropyl alcohol. A sample of pure isopropyl alcohol has the following percentage compositions: 60% carbon, 13.4% hydrogen, and 26.6% oxygen. 1. Determine the empirical formula of this whiteboard cleaning agent. 2. Determine the molecular formula of the whiteboard cleaning alcohol if the molar mass of isopropyl alcohol is 60 grams per mole. Let's take a look at the solutions. First, we convert the percentage into mass, and to do that, we're going to assume that the whole compound weighs 100 grams. And hence, those percentage signs will now be replaced by kilograms signs to convert that to mass, and hence we'll have 60 kilograms carbon, 13.4 kilograms hydrogen, and 26.6 kilograms oxygen. Next, we're going to calculate number of moles of each element. Number of moles of carbon is equal to 60 divided by 12, which is mass divided by molar mass, which is equals to 5 moles. And number of moles of hydrogen is equals to 13.4 divided by 1, which is equals to mass over molar mass, which is equals to 13.4 moles still. And finally, number of moles of oxygen is equals to 26,6 divided by 16, which will give us a number of moles of 1,663 moles. Now, to find the empirical formula, we divide those number of moles by the smallest number of moles, which in this case is that of oxygen. And hence our empirical formula will consist of a carbon which is equal to 5 over 1,663, which is the smallest mass, which is equal to 3. And that of hydrogen will be 13,4 divided by 1,663 again, which is 8. And finally, 1,663 divided by 1,663 of oxygen will remain 1. And hence the empirical formula of that whiteboard cleaner will become C3H8NO. Now let's move on to the second part of the question, calculating the molecular formula. The molar mass we get from empirical formula, or the one we use empirical formula to calculate, is equals to 3 multiplied by 12 plus 8 multiplied by 1 plus 16, which will give us a value of 60. And if you look at the question also gave us the molar mass of 60. And hence this means that the ratio of molar mass of empirical formula and molar mass provided by the question, or the actual one, is 60 divided by 60, which is 1. And hence the empirical formula and the molecular formula will be the same, and hence the molecular formula will be C3H8O still. Now let's move on to percentage purity. This is the final use of stoichiometry in this chapter. This is the percentage of a specific desired chemical compound in an impure sample. It tells you how clean or contaminated a substance is by comparing the mass of the pure chemical to the mass of the mixture. Percentage purity formula is as follows. Percentage purity is equal to mass of compound divided mass of sample, all multiplied by 100. Now let's take a look at an example. Seashells collected from a beach contains calcium carbonate along with sand and other mineral impurities. Tabo wants to determine the percentage purity of calcium carbonate in a specific shell sample. He finds that the raw shell sample weighs 8 grams. After performing an experimental analysis involving heating, he finds that the combined mass of purified calcium carbonate and the crucible is 6,1 grams. The empty crucible itself has a mass of 0,9 grams. Calculate the percentage purity of the calcium carbonate in the seashell. Let's take a look at the solution. First, we're going to calculate the mass of the desired product, which is calcium carbonate. And to do that, we're going to go on and say mass of calcium carbonate is equal to 6,1 divided by 0,9, and that will equal to 5,2 grams. That is because the 6,1 value is the combined mass of crucible and calcium carbonate after the reaction, and we are only interested in the mass of calcium carbonate, and hence we're going to subtract the mass of crucible. Next, we're going to calculate the percentage purity, and hence substituting everything we know to the percentage purity formula, and we'll get percentage purity is equal to 5,2 divided by 8, which is the mass of the sample or raw sample, multiplied by 100, and that will give us a percentage purity of 65%. And that is how you solve that particular problem. Now let's move on to the final part of this lesson. Volume relationships in gaseous reactions. Ammonium nitrate is widely used in South African mining sectors as an industrial explosive agent. When heated under confined conditions, it decomposes rapidly according to the following balanced chemical reaction. If a mining engineer detonates a charge containing 835 grams of pure ammonium nitrate, what volume of oxygen gas would we expect to produce at standard temperature and pressure? Let's see how we solve this one. First, we're going to go on and calculate the number of moles of ammonium nitrate, which is our reactant. And we're going to go on and say number of moles equals to mass of mole. And we're going to go on and say number of moles equals to mass over molar mass, like we've always done, and substituting in the mass and the molar mass, will have 835 divided by 14 plus 4 plus 14 plus 16 multiplied by 3, and that will give us a molar mass of 80, and hence we'll have 835 divided by 80 to give us number of moles of 10,44 moles. Next, we're going to determine the mole ratio, and hence ammonium nitrate to oxygen, which is reactant to product, is 2:1. And to calculate the number of moles of oxygen produced by the available ammonium nitrate, we're going to go on and say number of moles of oxygen is equal to number of moles of ammonium nitrate multiplied by mole ratio, 10,44 multiplied by 1/2, and that will give us number of moles of oxygen of 5,22 moles. And hence we're going to go in and substitute that into the volume of the STP. We were introduced to this formula earlier in the lesson, which states V is equal to 22,4 multiplied by number of moles, and hence substituting in our number of moles, we'll have 22,4 multiplied by 5,22. That will give us a value of 116,928 dm cube. And that brings us to the end of this lesson. Thank you for joining me. Please like the video if it has helped you out. It helps the channel out as well, and comment below on which chapters you want me to cover next. Until next time, take care.